Good evening to all the attendees who have gathered here today to listen to this special public lecture, which is being organized by the National Academy of Sciences India Delhi chapter and MHRD-Institution Innovation Council, Deen Upadhyaya College, under the aegis of DBT Star College program. But this special public lecture is the last of the lectures which have been organized jointly by the NASI and the Deen Upadhyaya College, and it is part of the Golden Jubilee commemoration year celebration of the DST's establishment. And so these celebrations are going to take place throughout the year, that is from May 2020 to May 2021. And today we have with us Professor Biman Bagchi, who's a fellow of all the science academies and also the National Science Chair, Honorary Professor at Indian Institute of Science, Bangalore. And he'll be talking to us about our voyage through time dynamics at molecular length and time scales. So as a customary, I'll introduce Professor Bagchi. He's a well-known internationally in the field of physical and biophysical chemistry, especially in chemical dynamics and relaxation phenomena. Many of his papers have made huge impact in the arena of science. He obtained his PhD from the Brown University, Rhode Island, USA, and subsequently carried out post-doctoral research work both at the University of Chicago and the University of Maryland, USA. He has received many accolades like Shanti Swarup Bhatnagar Award, 7th GD Birla Award, Goyal Prize, and TWAS Prize, that is the Third World Academy of Sciences in Chemistry, and most recently the prestigious Humboldt Research Award in Theoretical Chemistry. He is an elected fellow of all four major academies of India, and he has served as a Dean of the Faculty of Sciences in the IISc Bangalore. He has been in the Advisory Editorial Board of several journals, including JCP, JPC, CPL, and Chemical Physics, Elsevier. In his academic career, Professor Bagchi has published nearly 470 papers in reputed journals and has also authored two well-known monographs published by the Oxford University Press and Cambridge University Press. And a third major text on statistical mechanics has been published by Taylor and Francis and CRC Press. He has authored 25 major review articles, including 6 feature articles in Journal Physical Chemistry, which are partly pedagogical and influence generation of physical and theoretical chemistry. Journal of Physical Chemistry brought out a successful patent in 2015 to felicitate Professor Bagchi. Recently, he received the 2021 Joel Henry Hildebrand Award in the Theoretical and Experimental Chemistry of Liquids by the American Chemical Society. With these words, I request Professor Bagchi to kindly share his screen and deliver his talk.
Thank you very much, Professor Saxena. And it's really a pleasure to thank Manoj because the nice, kind, and gentlemanly way he has contacted me and I've gone about it. It was very pleasant. Only bad thing is that I'm not being able to meet him in person and give this lecture in person. But that's what it is, and that's how we'll go. So I have slightly changed, only very slight. Talk has remained the same because I think what I'm going to talk today, I think most of you will like. This is about evolution of time and length scales. Both have undergone tremendous amount of evolution in the last, say, half a century. And that has helped us to understand huge amount of phenomena. I myself became aware of the huge impact only in late 1980s or 1990s when I began to understand what's happening after, of course, doing some work. So what I'll try to tell you is not just chemical dynamics. I'll talk to you about biology. Quite a bit of biology will be here today, and some physics. So I've taken examples of this voyage. It's a wonderful voyage that we have. I have organized in certain fashion with the help of my students. Some of them I'll show at the end. And it's simple. So we like it, I hope. And so, as I was saying, it is not just chemical dynamics, it's biology and many other things. So basically what happened, as our accessibility of the shorter and shorter time scale and smaller length scale became available to us because of laser, because of microscope, we started to study newer and newer things, and huge amount of new phenomena were discovered and understood. Old theories broke down and a new understanding emerged. Okay, let us go. So man's quest for time is old, is very old. So from very early time, you can just do a Google or something or internet search, you'll find that all these old clocks, sun clock, and Egyptian has their own way. We Indians have a wonderful way to do it. It started all with the flow of rivers, tides, and movement of sun and planets. In ancient India, so man was always thinking how to get a time, how to fix a time, measure unit of time, so that I can describe certain interval. In India, we had an interesting method to measure time called Shanatoni, where the unit was wink of an eye. This is a wonderful thing that, you know, and then in wink of an eye, we kind of, our ancient forefathers, like for example, it was religious significance. Remember, in case of Brahma, one wink of an eye in many million years. Okay. So, but however, you can, people have really measured out with the unit wink of an eye, which is almost a second, then different times. You know, it is called, the method is called Shanatoni of time. You can read about it. Now, from those old early days, when man's quest for time, when there was no measurement, you know, mostly about, we depended on these kind of things, we went a long way. We came a long way. And in the voyage through time, what was helped in physics and chemistry and biology is the spectroscopy. So I'll talk some about spectroscopy, and the spectroscopy is actually, these are the kind of time scales that the shortest time scale is that measured, that involved in many experimental studies now in biology also, is electronic coherence and decoherence, how a wave function becomes out of it. That happens 10 to the power minus 15 second is a femtosecond. Then there liquid collision, which happens about 10, 20 femtoseconds. Then there is one very surprising thing that was discovered in early 1990s, is how fast an electron or a proton or any ion can get solvated. One thought it is a slow process, but it's extraordinarily fast, faster than molecular rotation. Then there are these very important biological reactions involving isomerization. Like when you open your eyes, there's a proton pump that starts in halobacterium membrane at the C13 position, and that is 200 femtosecond. Then there's a vibrational relaxation, which is involved in bond breaking. Photosynthesis, we'll talk a little bit about that. Enzyme kinetics, which is slow. Protein folding, which is slow. So there is a very fast things which are happening in femtosecond time scales, and you have very slow things which are a millisecond, second. And we have progressively moved from right of my screen to the left, and then again come back. So this is interaction between fast and slow is a wonderful, wonderful kind of a journey. It was succinctly put by George Porter, that man's race with time. He visited Bangalore, gave a wonderful lecture, I think in late 1980s, and this beautiful thing. He had a beautiful diagram about, I could not find that, how time has evolved. But I remember this quote that Porter gave, that man's race with time started with Manfred Eigen and won by Maxwell. Both are Nobel laureates. Porter himself is a Nobel laureate, and there's a wonderful quote. I was giving this talk as a special lecture in the award lecture in Caltech, and Maxwell didn't know of this quote, so he came running to me after the lecture, and he wanted to know more about it. But I don't know where it is, but I heard it from the man himself. So Manfred Eigen, let me tell you, is a very interesting man who founded Biophysical Institute in Göttingen. Manfred Eigen shared Nobel Prize with Lord Porter and Norris Porter, Manfred Eigen, who was the Lord Porter gives him this, Lord Porter's language by and large, who gave he was intrigued by the statement in a book that some reactions are too fast to measure the rate. So he set out to measure this rate, and Porter evolved fast time which could measure microsecond, the system of flash photolysis, temperature jump, these methods of creating disturbance or perturbation, and then measure the rate. So actually the technique, the strategy was set at the very beginning. In order to measure a rate, you have to perturb it, and then you measure the response. So this is what is essentially we call the response, dynamical response of a system. Okay. Now I'll have a few things that now voice through time in spectroscopy, which is essentially the great fun to go through, and all the Nobel Prizes. So on the A, I told you the ancient clock. Now let me tell you a story. I'll tell you several stories, and I'll show you pictures of horse, monkey. I don't have donkey. Yeah, at the very end, I'll show you a donkey, but many other what other animals? Oh, cat. But okay. Now this Mayavich, Edward Mayavich was a very famous photographer in Palo Alto, not too far from Hollywood, and that was the beginning of the fast photography. So the Stanford, he was the mayor of that time, Palo Alto. He and the other person had a wager, a bet. And bet is the following: during the motion of a horse, is there any time, any moment where all the four legs up in the air? Well, Stanford said no, other guy said yes, or maybe other way around. So they had to fix it. And there's a big wager, $20,000. They are rich people. Those days, $20,000 was a lot of money. So look at the 1872, around that, 1870 of that time. Stanford was already just about established. So they employed or asked the help of Mayavich to do that. And Mayavich did a wonderful thing, which is the beginning of time delay experiments. And this is the first measurement of fast time. What he did, he put 16 cameras at regular intervals, and all of them connected by one string. So when the horse just entered the fast camera, pull the shutter. The strings are such that they were different lengths. So the camera shutter went up one by one at a regular time interval. And he could take 16 pictures. And yes, you can see one of them, all four were up. And this is the beautiful a movie made by those 16 frames. And that was the beginning of the movie industry. And no doubt Hollywood became such a big place. Palo Alto is just off the a few hundred miles near San Francisco. Okay, now these are the three gentlemen, Manfred Eigen, Norris Porter, and George Porter, who got the Nobel Prize for the first thing that I say, which are microseconds. Continuing my voice to time, then there were the laser spectroscopy by Blumbergen and Shaklow. Then there's the high resolution electron spectroscopy, which will come later. Then another greatly cherished, greatly respected Nobel Prize is Ian Lee Herzberg and Dudley Herzberg and Polanyi, and who used the laser. By that time, nanosecond laser. This was experiments done in 60s, late 60s, 67, 68. And they use nanosecond laser combined with vacuum technology. So a molecular beam apparatus, and they could measure the nanosecond time scale of dissociation association of methyl iodide or even alkali iodide, sodium iodide in gas phase. So this was nanosecond spectroscopy. So we have gone down to 10⁹ second. And that was the first measurement. And I recommend students please read the Nobel lecture of Dudley Herzberg. It's a wonderful lecture. He just tells you how important this was. There are a lot of theoretical calculations by then by quantum chemistry. What would be the rate? What would be the potential energy surface of a binary dissociation reaction? We'll talk about much more complex dissociation reaction a little later. But this simple diatomic gas phase reaction, the chemical, reaction at the surface, which you have read many of the books in physical chemistry, in Eyring and these people, they could really get that surface and they could get the rate, which agreed quantitatively. Okay, that was 67 to 70. Now there are theory of electron transfer reactions were done by, we'll talk about a little bit more, the Nobel Prize in 1992. That Nobel Prize also came from the calculation of a rate. This rate now in the picosecond. And it was predicted by picosecond and nanosecond, predicted by great Rudy Marcus. But Rudy's prediction was initially said it doesn't work, but then it turned out to work and he got the Nobel Prize in later. And then the femtosecond credited to Ahmed Joel, whom I already quoted, that Lord Porter's quotation, that he could, in organic chemistry, you always talk of transition state. But it is something which was so fast, just like Manfred Eigen's case, to detect. He developed some beautiful techniques, femtosecond laser pulses and molecular beam and all that, so he could get that, really detect the transition state, the presence of the transition state, characterize the transition state. And here's the Voyage Through Time, a part of my title taken from the Ahmed Joel's title. Okay. Now, these are very interesting things. So I'm talking of transition state, which in the calculation of both Rudy Marcus and Ahmed Joel, this intermediate state, which chemists call transition state. It comes from the Arrhenius and all these people of Ostwald and all these people. Those are the fathers of physical chemistry in the very early of 20th century to describe the temperature dependence of a chemical reaction rate. Now, how do we understand transition state? So it is the example given is that there is a cat. You take a cat in the world, very happily, philosophically looking, you just give it a push suddenly, then this cat will fall. But interestingly, it falls just in the wrong way in the beginning, then it turns around, and then it in the fourth frame from the left panel, it has almost reached halfway, and then it turns down and lands perfectly. You can do that experiment if you have a cat. They'll always fall like this. So the fourth from the top left panel is the transition state. So in the case of cat, we can detect it, but in the case of chemistry, it survives for a femtosecond. It was very difficult to. That's why it was a monumental achievement, and that's what Lord Porter alluded to in his lecture at Bangalore. So I have now discussed too briefly about the voyage through length. The time now I'll tell you something about voyage through length. Then I'll combine these two and discuss some very interesting developments over the last 10-15 years. There will be many examples, but everyone will be short and everyone will be pedagogical. Everyone will be picture based. So it's just to enjoy, So voyage through length is through microscopy. And this is what the length, it is the other way around actually happened. Length scale started from macroscopic and we went to the left. And how do we measure it? Here also, there are many hypotheses just in time. Many ideas developed but not verified because we didn't have the length scale resolution. Okay, let's see how we went wrong. This is an interesting picture of Aristotle given by Aristotle. Aristotle is one of the fathers of philosophy, wonderful person, but he got many things wrong. Here is his view of the universe with Earth in the center, and he got from the intensity. Sun, he realized one thing: sun is very big. That that's why sun he put, though it's so big, it is little far. He put it. And then one more thing Aristotle got wrong. It was amazing because Aristotle was a thinker. He came out with the great theory which survived for quite some time, that a woman has 28 teeth while a man has 32. I think the poor devil did not open the mouth of a woman to check out probably and count it. Now, on the ISO, but that was the first length scale that in the left, in the not in the teeth, not my truth story, on the Aristotle, and then the first thing, the Shakespeare person looking like a Shakespeare is not Shakespeare. This is Zacharias Janssen, who passed the two lenses together and made the first compound microscope to start looking at the small objects. And then first man to make an use of a real microscope was this Anton von Leeuwenhoek microscope, and he could go down to few thousand angstrom. Now the going below the wavelength of light, below few thousand angstrom, was done by Richard Zygmundi, and who got Nobel Prize 2009. And now phase contrast microscope, when it was done, people could for the first time, this by Fritz Zernike, he did many other pioneering contribution. One could look for the first time cellular image of a biological cell. That was possible because the phase constant microscope. It was possible in 1940s. He got Nobel Prize in 50s. Electron microscope, which heralded a completely new technology. Now we have entered in the era of material science. And then electron microscopy, scanning tunneling microscopy, scanning probe microscope, all these beautiful things. And each of them got a Nobel Prize. And with that, the understanding of materials evolved and beautiful results came out. You all know so many structures and so many Nobel Prize, so much work has come into this. So, so my voice through length take me from the Aristotle's universe to sub or angstrom level. I did not have one slide I should have had is the X-ray. So X-ray crystallography should have come around early 19th century, almost at the time of Arrhenius and Van 't Ostwald, when one started to get a length measure from X-ray crystal. That happened, you remember, in 1890 or so. That slide should have been here, and the Rongen Nobel Prize should have been here. Okay. Now, we have come, so I have described you in a very nutshell, in a very simple way, what is the voyage through time. I have told you voyage through space, but what we really want to know, the voyage through space and time together. We always wanted to know how molecules move in space, how much they move, and what time scale they move. For example, in isomerization reaction, like a cis going to trans or trans going to cis, we want that cis-trans isomerization. And that's the rotation of a bond. So phenyl groups go from trans to cis position. So it rotates like this. I want to know how much it rotates and where does it go, what is the exact angle, and I know the time scale. And now take what I've shown here on the figure is a protein folding. In a protein folding, a large amplitude motion takes place. A protein collapses to the native state. There is a change of radius, there is a change of dimension, but more important that a lot of movement takes place. Yes, change in radius may be 4 or 5 angstrom, but more importantly, the hydrophobic groups come together from the core. Now we want to know what is the time scale of protein folding. We know that it takes place usually seconds or so, and we want to know how much it moves. That was possible. That was possible by microscopy, because microscopy gives you a static picture. While laser and dynamics was giving you a dynamic picture. One has no temporal resolution, other has no spatial resolution, SPATIL, spatial resolution. Single molecule spectroscopy, which got Nobel Prize a few years ago, through the work of Moerner and other people, and all over the world in physical chemistry, people worked in biology, people worked in that single molecule spectroscopy combined the fluorescence spectroscopy, the laser spectroscopy with microscopy. That is the wonderful evolution that has taken place, and that has really, really helped answering many questions in biology and still answering. Okay, so few chemical processes that I'll not go into detail into that, but where we could study. One is bond breaking events that I already told you, that was the Dudley, Herzberg, Yaley. Then isomerization, that many laser, many things happened. Electron proton transfer reaction, our Rudy Marcus, and then later Ahmed Zuhail. rate in complex systems. And these are the new things that has happened. That with the combination of spectroscopy and microscopy, with the resolution that we have now of time and space, the length scale, we could study enzyme kinetics for the first time, photosynthesis, that I'll talk a little bit, electron in water solvation. These are the wonderful, wonderful things that came, which was not possible before 19, say, for example, 90. Okay. So now I told you a lot about experiments. I talked about lasers. I talked about time resolution. I talked about microscope. But what about theory? What theory we use to do that? Okay, the theory is used uniquely and is statistical mechanics. Statistical mechanics with certain help from quantum mechanics. Statistical mechanics is the one that allows you to convert your microscopic information in terms of intermolecular interaction to macroscopic observables like free energy, viscosity, rate of a chemical reaction. All these things are done by statistical mechanics. It's a huge discipline. It is a, I always call the theoretical physics and chemistry and the two pillars. One is the quantum mechanics and the statistical mechanics. Unfortunately, in India, statistical mechanics, particularly in chemistry, is really neglected. Of late, things have improved, but this is a way to understand biology. This is a way to understand material science. Who are the fathers of, they were before Nobel laureate prize, and they were probably far beyond Nobel Prize, these guys. James Maxwell, who started kinetic theory, developed the electromagnetic theory and kinetic theory of gases. Kinetic theory of gases is the one that we are interested here. Then great Ludwig Boltzmann, early days of statistical mechanics, and then the great William Gibbs. Boltzmann has the thing, and I have shown there, entropy and these entropy and number of configuration states, multiplicity. This we know Boltzmann formula. Then building on Maxwell and Boltzmann, Willard Gibbs did that. Now so the basic idea then is that what they pioneered at that time, and before any really had any information about it, really fabulous kind of development. They imagined the kinetic theory of gases when everybody was doing continuum. The matter is made of atoms and molecules. Okay, Dalton has done that, but in gas phase people are still not doing. In liquids people are not doing that. So the Maxwell's distribution of velocities, and then Boltzmann took it forward, his kinetic theory of gases, and then between them they developed the theory which I'm not going to go into, but they are the father of statistical mechanics. Now tell you about Robert Mulliken, about the saying that what is the contribution of Willard Gibbs? He did for statistical mechanics and thermodynamics what Laplace did for celestial mechanics and Maxwell did for electromagnetic theory. That means he himself put it into a high-level theoretical structure, which later went into many things, and I'll be using that. So with my homage to these three gentlemen, let me go ahead. So what Boltzmann did, in his work was latent these postulates, which was then further formulated by Willard Gibbs, that first one has to define averages. Specific, it is an average. Energy of a system is an average. Entropy is an average. Average of what? Many molecules they are moving around. So I need to consider the movement of the molecules and their average over that. So there is something called time average. There is an alternative way of doing it called ensemble average. I'm not going to go into that. Right now, there is an NPTEL or SWAM running a course by me on basic statistical mechanics. It is running now. Basic statistical mechanics, NPTEL, national portal. And you can, it is freely available, the course. You can join it, and please read the first, students read the first, listen to the first 3 or 4 lectures of my course. There I have described all these things. So second postulate is a wonderful postulate, comes from probability theory, that equilibrium probability, all microscopic states are equally probable. They had no other way of doing that because they assumed to be equal energy and all equal probability, and they turned out to be correct. Thank God. And these two are connected by ergodic hypothesis that all the microscopic states are accessible. And that is Armed with two postulates and one hypothesis, they build this huge discipline called statistical mechanics, both equilibrium and time dependent. Now entered Einstein almost immediately that time, 1905. So around the same time, he realized something. Brownian motion, with the motion of a pollen. When you looked under a microscope, it was so handy. People have the optical microscope then. They looked into pollen, and Robert Brown saw this pollen moving continuously. First he thought they're living. But then all different pollens, they all move, dry, things. Then Einstein, and he said that so this is a property, inherent property of the liquid, because it is independent of the characteristics of the large object suspended in water that he was observing through his microscope. So then Einstein formulated a theory that he said, okay, these are random collisions with the solvent, and this last equation, diffusion is 1 over friction, is the Einstein equation, and the definition of diffusion measured that played a very important role in understanding of the rate that we are going and length scale. So look at diffusion, it's very interesting. It is already in it, genesis of my talk. It is mean square displacement, how much a particle moves in time t. So displacement by time, that is a very universal characteristics of the system. Why universal characteristics? Because this is a statement also of the conservation of mass. And this is how we describe rate and many other things. So these two equations of Einstein, started the way of time-dependent statistical mechanics and fluctuation theory. And here I again write an equation. It is Drunkard's random walk what turned out that Einstein theory is essentially already was well known in a different context in probability theory in 19th century. And that is called the random walk, and this is a Drunkard's walk, and which is, I hope you can see a little bit of that. This is two particles, Brownian particles suspended in say liquid water, and they are randomly moving around. You can take their displacement and del x squared divide by time, and lo and behold, that becomes a linear function of time. This is amazing. This is an amazing amount of beautiful science it is. Okay. Now, all these theories that were developed was now employed by Rudy Marcus to explain in 1956 one of the very major unsolved problem of the time, how to calculate the rate of an electron transfer reaction. And another thing is the rate of electron transfer reaction was found to vary over a wide range. Why was so? So there was a theory by Louis B. That's what I was saying, that new results started coming out, and that was the immediately after Manfred and Porter. New started coming out, and one was there are already theories, and as I told you, these new experiments and gave rise to new theories, and many theories fell apart. So Levy had a theory of how electron transfer takes place between donor and acceptor, like iron and iridium, or can be cobalt 2+ and cobalt 3+, and he had a theory that it has to be excited like a radiationless, like a radiative transfer. Rudy Marcus said, no, the way it takes place is very different. The molecules on its fluctuation, the fluctuation concept introduced by Einstein, undergoes intermediate state, which is the transition state. So here a transition state is a collective state. It's very interesting. A transition state is created by the solvent by moving its dipoles. And that transition state is reached at much lower activation energy and facilitates the transfer of electron from A- to D+. I think it's a donor, okay, D+, it's wrong. Okay. Now he derived some beautiful equations which are well known, are still used. I just was talking with somebody and he used this equation to in a device, in a glass. Deposited paper deposited glass. There's Samsung uses on the mobile. So they use Marcus theory to study the electron transfer. Many ways that is used. So these are some beautiful equations, and this is the our chemist favorite way of telling a free energy, how activation barrier, and they did definitions of lambda x are given here. I'm not going to go into that. But one interesting thing is that it has this peculiar dependence, exponential minus This is the reorganization energy, and this is the free energy gap between the donor and the acceptor. The strange dependency found, and which was very difficult derivation it did. Of course, later one I did some very simple derivation, but that predicts that if I vary the stability of the donor and acceptor, which is done by ionization potential and electronavity by changing different groups, this will be a inverted parabola. That means it would be like this, like a Gaussian kind of a thing. And then people tried to find it. People tried to find it by doing all kinds of experiments. People couldn't get it, and poor guy didn't get Nobel Prize in 1984. However, then laser came around that time. So this pioneering experiment was done in University of Chicago. I went there just when this experiment was just done, and there was so much excitement in the air. And this is the Miller-Caldera-Claus, a paper where he showed indeed by varying delta G, you find they reproduce these results by doing different things and the electron transfer reaction. This is an amazing success story. But in that success story, two important things come into play. One is the length. They varied the length of electron transfer from one place to another, and the time. We are measuring time here. So again, the length and time, the ability to get the time through laser of nanosecond. Look at the bottom is already about 100 picosecond. And I told you it varies over huge range. And that's a logarithmic scale on the left. Okay. Then, at the same time, again in Chicago, those days Chicago was really the Mecca of doing this kind of physical chemistry. Graham Fleming with the ultra-fast laser, which he was gifted to him actually. He was to do this experiment. He was very proud. I knew him then that he got a free laser. And he measured how long it takes for a charge created optically. So laser is used to create a charge distribution in a molecule. Then it becomes more stable, and he could measure that. And that turned out to be 100 femtoseconds. 100 femtoseconds. First part was 50 femtoseconds. That's the graph giving here the experiment and theory and all the simulations and all these things. Now, the solvation dynamics played an enormously important role. It is just like going back and forth. So the basic solvation dynamics I excite, and this is, by the way, this figure was drawn in front of me by hand by Amir, and you can see the experimentalist at work. So he excites in the purple, and then as the molecule relaxing on the upper free energy surface, it is emitting light, and the light going towards the lead. So it is where energy is coming down on the inside panel. And he could measure, Graham could measure the time of that. And that is, as I 200 femtoseconds. And that is that the fact that solvent polarization, solvation can undergo this ultra fast, had an enormous impact on our understanding of and that then started new kind of theory of people start talking, okay, now not only I know transition state, I can measure how long a molecule stays on the transition state. And there it is shown on the left, the figure that there is, I can talk about residence time. And they are all in a sub-picosecond level. And that played a very important role in explaining many unsolved problems. Like it was very old work, I told you, done by experiments were done by Fleming, Hochstetler, Eisenthal, and Rettig, that you see the theory, black line, and the experiment that, and one can now explain with new input, the new theory that was developed. Okay, now I'll go a little bit and spend 5 minutes on my end by telling you a story about a monkey, the protein folding, understanding through chemical kinetics. And again, look at the length and time scale. So protein problem is this, as I told you already, it's the length scale, predetermined contact formation. And it is different from liquid to solid phase transition in the following sense. It is much more entropically driven, entropically demanding. So if you have a classroom, boys and girls, and they're randomly placed, now you fire a cracker and everybody goes out. Now you tell them they come back, it's nothing. Then they come back and you want them to be, again, same neighbors. The girl should want the same two boys on his left and right. This is different from melting and freezing. In melting and freezing, you can do many times sodium, but every time nearest neighbor least changes. But in protein folding, nearest neighbor least remains the same. And that is highly demanding entropically. That's why protein folding is such a protein problem. So the great experiment on this was done by great Anfinsen, ribonuclease, and he took the ribonuclease. He did also lysozyme. He used urea and Markov tunnel, beta Markov tunnel, and he there are 4 disulfide bonds, and he broke the disulfide. Shown in yellow on the left, and he broke that, and it became unzipped. Then he removed the urea. It again, same predetermined contact form. It again formed, and there's no reason to form. Like no reason to form the one distant along the contour, along the chain to be formed again. But that's exactly what happens. Like 85 again, 95 again forms with 40, 84 with 26. Again the same contact, and it becomes biologically again it's biological activity. What makes it do so? This is a very interesting question. Anfinsen argued that it is because of the stability. Leventhal then asked, Cyril Leventhal asked a beautiful question, become Leventhal paradox. How long does it take for a protein to fold into its native state? He said, okay, I'll do a whimsical thing. He said that 101 amino acid I take. Each amino acid can have many configuration states. So I just take 3 states. Then I have 3 into 110 configurations. Now, if the protein samples all the configuration at 10 to the 13 per second, very fast, even then it will take 10 to the 27 years. Why it has to sample? Because the protein must know, if unconventional hypothesis is correct, that that protein is stable. It has to sample at least 1% to know that indeed I am the most stable state. You know, if somebody is rich, you need to know some property about that rich man to know he's rich, and I'm poor. So protein folds in time scale of seconds and even milliseconds, and that was the paradox. How does it do it? Okay. Enters Shakespeare and Richard Dawkins, blind watchmaker. I'll not tell the story of my discovery of these things because I don't have time. But it's a beautiful story. In order to explain the evolutionary biology, so this has the following background. In the 19th century, there are the famous theologists who used to go around in England telling everybody that, look, if you are traveling in a forest and you find a beautiful watch, you pick it up, you look at the watch, it is so beautiful, so systematic, running so well. So somebody must have made it. Look at the nature, it is so beautiful, flowers are identical and all these things. So somebody must have made it. So we was telling that Darwin's theory is wrong, there's a God who made it. Richard Dawkins wrote a book, Blind Watchmaker. He said, yes, there is a maker, there is a watchmaker, that's a blind force of nature. And he gave this a beautiful example from Hamlet of Shakespeare, one line. Methinks it is like a whistle, which has 28 characters, 27 possible choices, random attended by a monkey, is 10 to the power 14 keystrokes. But now, if you make the rule, so it is like Leventhal paradox. A monkey will never get it. Forever, he has to go on typing. But if you make the rule that once monkey hits a correct key in correct place, you don't change it anymore. And that then it's a few thousand strokes. And I did that experiment. This is beautiful. So now consider, go back, solve the Leventhal paradox. I consider 2 states per bond. But now I made correct to incorrect and incorrect at different rates because they are different free energy. Then I calculate the random state. And I find, yes, little bias gives you reduce the time to dramatically. From years and years, 10 to the power 30 years, it comes down to few seconds. Very small increment. Essentially also the law of large numbers. So the Leventhal paradox is essentially the blind. It is in every textbook now, not only Rupert Stewart, also in the whole chapter of Leninger. The protein folding is written on this. Okay, now I go through voice to space and time. I have 5 more minutes or so. Single molecule spectroscopy, a little bit more detail. This is a beautiful picture of Warner, picture where he on the tetrazine on paraffin wax, and pictured by after shining light, and each peak is from a molecule, one molecule. Kerosene or tetrazine, I don't remember. Paraffin wax, one molecule. So it's beautiful to see the image of a single molecule. And this is what the famous Simon Weiss, that the ability to analyze individual molecules still amazes an honest and most jealous practitioner. But it has developed very new techniques. And the new techniques were that two things you had to do. You take a very dilute solution and then you use a microscope. So again, you could do that because your photon counting and optical techniques and laser were developed to pick out single photon, and microscope was allowed to zoom on. And then you do that and you you could do the protein folding. That means you can study one molecule because of this dilution and microscope, and then collection of optics, and you study it. And here the single molecule fluorescence. So here donor and acceptor, when they come close together, they die, which is coming down. But when you have a continuous laser source on, again, it goes back. So this is beautiful. Again, length and time. The transfer energy when they are close to each other, that is length. So by doing this experiment, I can find out what time they are coming close together. This is an ultimate kind of thing. So this is called FRET and fluorescence spectroscopy. Then this was used to enzyme kinetics. It was down to how a protein diffuses around DNA. There was a very interesting question. How does a protein find its, because when those of you smoke, your DNA gets damaged. And then there is this HOG1, this crystal structure. Then it goes around and finds and connects this deoxidized guanine from oxyguanine to guanine. How does it find it? That was the question. And is this sliding motion? How does it do? And this is again the experiment from Sunny's lab, showing that they can see, these are again little picture from each DNA protein complex, and one can find the rate of this. And then the question was that is it random or is it systematic in a trajectory? It turned out the way protein goes follows an ellipse. So it rotates and translates at the same time, and everything is coded in the DNA sequence. And then one can do a little theory, and that it works out beautifully. And the papers are these kind of papers available. Then we entered computer simulations and chemistry. Our great Ansu Rahman did enormous amount of work called Darwin Wright, and he gave the Nobel Prize. Ultimately came 2, 3 or 4 years ago, that the multi-scale modeling of complex chemistry, and that is like enzyme kinetics is the bond-breaking event. How does the magic happen of enzyme? And that became possible because of the single molecule spectroscopy and other things. I'll take 2 more minutes and I'll just skip through that. That's how the barrier decreases. And beta galactosidase is a very important thing that hydrolyzes lactose to put galactose and glucose going on in your body if you have tea or coffee right now. How does it happen? That was, it was really a puzzle, but single molecule spectroscopy showed us that is a rugged energy landscape. We begin to see how it happens. What are the configurational fluctuation play a role? There's not a single rate, there are many rates, but what you measure by Michael has mentioned, kinetics, then is a single rate. And so there are a lot of controversy on that. This is my Star Wars picture. And again, I said electron transfer reaction is beautiful, beautiful stuff that Rudy Marcus figured out, that how solvent can play a role to get you the and then there is now going on to study the beautiful stuff that these pictures, the fundamental problems of physical chemistry. This is my another talk, that how molecule rotate, like we can do nitrate ion. Before you couldn't do nitrate ion, that how nitrate ion rotates and how it couples to jump motion in water to get jumps. This is completely new. It just came out some last 2-3 years. So water jumps, that also is a new discovery, that the way water moves. But nitrate also goes with that. So these are beautiful stuff that you can find all these things there. So then one state, okay, now we started going really saying that, okay, we have done Coulomb's law. Is the Coulomb law valid in a molecular scale, length scale? No, Coulomb's law is not valid. So simple Coulomb's law, we call HCl, breaks down because of the interference at small length scale between positive and positive ions. The solvent despolarizes in between. And then positive and negative ions, and these are all came out. So this shown the breakdown of the simple Coulomb's law or screen Coulomb's first law that people use in computer simulation. So these are the many papers that came out. Okay, so I think this is last bit. the insulin dimer dissociation. We studied this, that how does a dimer, see, insulin is active as a monomer, but it is stored in body as a hexamer. So hexamer has to go to dimer to monomer. And that is the, we studied that how does it happen. First we studied, of course, hexamer, but I'll tell you other way around, how dimer dissociates. And that's a wonderful story. The dimer dissociates even when it is 5 nanometer apart, the center, surface to surface, 30 angstrom apart. Even then they know each other. That just came out in DNAs, and a huge number of water molecules inside. And those water molecules inside are different from bulk water molecules. So again, they are dynamically faster. So my length and time scale again. So this is what it is showing, that molecules are faster. If you look at the top panel, these molecules are showing their rotational time, their rotational rate. They are faster, surprisingly faster than bulk behavior. And there is a potential energy surface that one can find out, much more complex potential energy surface than we could do before. That number of contacts, hydrophobic contacts, and the distance between them, and we are calculating the rate on these kind of things. Then one did some insulin hexamer into the collaboration with the experimentalist. This hexamer is a beautiful symmetric thing with 2 zinc ions on the top and bottom, and the 6 insulin are held together, 3 dimers. We started studying it and said, what holds it together? We found it was 10 water molecules that hold it together. And if we remove those water molecules, then this is what happens. That if you remove the water molecules, then it just collapses, you know, this thing. Okay, this is, movie is not loading, and I hope it comes back. Little bit problem here. Manoj.
Yes, sir. You can share that video again, sir.
Okay, so
yeah.
I'll share again.
Yeah.
Okay. Okay. Share screen. Okay. All right. I think we go through this now. Go to the end. We will not show that anymore. So insulin hexamer and it came out in CNES big ways. And photosynthesis, again, beautiful. And the most important process on earth is called photosynthesis, how photosynthesis takes place. Huge amount of work that took place. So basically, question is that it is a femtosecond time scale. And its length is very small. Chlorophylls are separated by 12 angstrom. And it takes place in few hundred femtoseconds. Again, wonderful work was done by Graham Fleming and other people, and that gave birth to what is called quantum biology. That it is a diffusion versus localization. Is it random walk or is quantum coherence? And that is shown here. Diffusion will be like hopping, and quantum coherence will go like that. And there are a lot of work that has gone on to that. Okay, so I have told you huge number of things. This is a beautiful article, Physics of Life, the Dawn of Quantum Biology. And we have done some work. So the energy transfer from these things, and this is length and time scale again. And so I think these are the work done by, I've taken 5 minutes more, so I should stop. It was done by these students, which is Pooja, who did dimer, and they also ions. These are the last part, and the Shomok and Shayantan. Rajesh got to this, the photosynthesis supported by DST India, National Science Fair, and ISC. It has been wonderful to be in ISC, and this is my extended group. They did something for me last year, and now we started with one person, and now we have a family of about 100 people. All over with my grandchildren, we have I think 40-50 faculty members, and so I start in last few things. So one glance of a book, famous quotation by Carl Sagan, and you hear the voice of another person, perhaps someone dead 100,000 years. To read is to go through time, and then the 3 books that I have written, which my students always insist I show. The molecular reaction liquid, one is the water, and this statistical mechanics. That's the course we are giving now based on these books. And I have written some things for the students. Actually, my students put it together. My blog that I write, they are available in Kindle. This one I particularly recommend, How to Perform Well in Academia. Very cheap. It is something like 56 rupees. How to Perform Well in Academia, guidebook for young researchers. And then funny one I told you, I'll show you Donkey. The 3 donkeys of Malaysian, these humorous things, but also has a lot of articles on the 18th cross Malaysian Bangalore, very close to University of Science. And then I end by one famous poetry by Rabindranath, and that is English fast, which doesn't sound good, but I'll then do this is the last poem of Rabindranath, 13th of July, 1941, 7 days before he died. In Bengali, 14th of Shravan, died 22nd of Shravan. And how he wrote this beautiful one, God knows. So it is 7 days before his death. The path of thy creation thou hast strewn with deception, laid down thy web at depth for the naive inept. This arcanum, thy trial for the noble, for whom no darkness is terrible. The lodestar that guides him is from his own conscience. In Bengali, it's beautiful. Tomar srishtir path rekhicho akirno kuri bichitro chalona jale chalonamoi. মিথ্যা বিশ্বাসের ফাঁদ পেতেছ নিপুণ হাতে সর্বজীবনে এই প্রবঞ্চনা দিয়ে মহত্তরে করেছ চিহ্নিত তার তরে রাখনি গোপনে রাত্রি তোমার জ্যোতিষ্ক তারে যে পথ দেখায় সে যে তার অন্তরের পথ সে যে চিরস্বচ্ছ and goes on like that. Please read that poem. My beautiful institute, I'm so grateful to it, and thank you. And this beautiful Joel presented me this beautiful picture of his Nobel laureate. Thank you very much.
Thank you very much, Professor Bagchi. This last 1 hour, I've seen physics, chemistry, biology, everything being amalgamated they have been all molten together in a pot, and you have presented it so beautifully. I mean, this has been a mesmerizing experience for last 60 minutes itself. So this has actually led to few questions. So if you can just stop sharing, then I can.
Okay.
Yeah. Yes, sure. So I'll take up few questions.
Sure.
So the first one is, it's basically, I think, from one of the students is trying to understand what do you mean by electronic coherence and isomerization dynamics.
Two are different things, though they are connected at some level, deep level. We are not going to go into that. Isomerization dynamics, as I told you, we have in chemistry molecules which rotate. Like, for example, when you in the morning open your eyes, then in a membrane in your eye called halobium, halobacterium, and there is a molecule, large molecule, which sees certain position. The proton pump starts, but before that, light must be absorbed and a chemical reaction takes place. The chemical reaction, no bond breaking. It rotates. So isomerization is like, consider a carbon, a double bond, another carbon, and you have a benzene ring here and hydrogen here, and benzene ring here, hydrogen here, and you rotate it. So cis and trans are, when trans, the big bulky groups are opposite to each other, diametrically opposite, and same side when they're called cis. So that reaction, where no bond breaking, is very fast. And that is why it has become the prototype when laser people started studying. And now electron coherence. Electron coherence is something, for example, the photosynthesis is a very good example. I create an excited state. There are, say, 10 di molecules. All of them can excite. Now, but they are coupled to each other. So you have two things. Energy that you give is connected, is localized and resides only on one of the di, and then jumps from one to the other. Otherwise, what happens? Since they're interacting, energy is actually shared. The wave function is distributed over that. So the eigenstate of the system involves contribution from all the molecules. That is an example of coherence, quantum coherence, and that plays a very important role in superconductivity and metal insulator transition. That's what I quoted Phil Anderson. So Einstein was the hopping picture, diffusion, but the quantum picture is that. So the idea is that photosynthesis is so efficient. As I asked, why photosynthesis is 100% efficient, where we cannot do more than 20% in lab? That because of the quantum coherence. That is the hypothesis, that when you create an excited state already knows there is a trap, which is the reaction center, which is downhill. So unerringly it goes there. So no energy is lost. Okay. So quantum coherence, electronic coherence is essentially when the electronic wave function is extended over many molecules.
Okay. Okay. I'll take up the next one. What is the time scale of atomic de-excitation?
That is very, very fast. Of course, depends on the coupling. So say this is what again Einstein comes back: spontaneous emission and a stimulated emission. So if I excite and the tail of the excitation remains, that causes stimulated emission. Then it comes back immediately in femtoseconds. Otherwise, you say molecule naphthalene, you excite it, it hangs there forever. You know, this I should tell you, we have one little very nice story. Graham Fleming, this is experiments, and some people were on solvation, some people were criticizing that he did not measure solvation, instead he measured vibrational relaxation or de-excitation, as we are talking. Graham told me on our tea on his home, very nice thing. He was very upset. He said, Biman, when I was doing experiments with Lord Porter's lab, he's a PhD student of George Porter, you know, we did this naphthalene and we knew that the naphthalene stays there forever. So that is very nice. So yes, in molecule, it can stay for nanosecond, even 10, 20 nanoseconds, atoms less, but you need a ladder. Energy has gone up. You need a ladder to come back. So the ladder is the coupling.
So the next one is by Chirag, and he's asking that what is your opinion on sub-femtosecond, attosecond, or maybe even shorter ones, that is zepto or yottosecond scales from a dynamicist point of view?
It is extremely good question, people. I see increasingly more and more attosecond experiments and labs are being set up. And when I was there in visiting 2 months, I told you in Amit Zuel's Caltech, they were trying that. The reason is that they wanted to see bond breaking. He has seen chemical reaction in a way, but now he really wants to see directly a bond break by electron diffraction. That how electron gets separated, you know, this is very, very nice. But he wanted to see how electron density between two bonds get out. That needs an attosecond experimental technique. Okay. Now, the attosecond has a problem. The person who is asking must be knowing. The shorter the laser pulse we go, it becomes broader in energy by uncertainty principle, the relation between. So your accuracy of excitation goes. That's what I told you, the Amit Zuel's example, that their energy is so large that that breadth will not harm you. But many other experiments like vibrational relaxation, I cannot do it attosecond. Maybe even isomerization, I'll have difficulty. So it has its limitations, but it also has its use. So I am, of course, positive about any theoretical, experimental and theoretical development. I think it's a wonderful thing. And I see a lot of people are doing, lots of labs sending me requests for postdocs and students. So I think it's a nice thing. It's a good thing.
Okay. The next one is any practical theory available to compute orientation relaxation time in binary polar liquids?
Sure, that's what we do. Yeah. I don't know who asked it, but it's a, like we did nitrate in water ethanol binary mixture, and the dynamics changes from pure water or pure ethanol. And the easiest way to get these days is the computer simulation. That's what we mostly do, but you can also have a theory, which we developed called mode coupling theory, very sophisticated theory. And we have series of papers on that published in Journal of Chemical Physics, Journal of Physical Chemistry. They're pretty well-known papers, so you won't have difficulty of finding them, including there's a huge perspective, JSCP, Journal of Chemical Physics perspective, some 24, 25 pages came out last year, where we exactly on this kind of things, the rotation, relaxation of nitrate ion, sulfate ion, and those kind of things which people never talked about it. And I told you, these are the things people are now talking, because we have one technique called two-dimensional IR spectroscopy. extremely difficult experiment with femtosecond laser pulses. Infrared spectroscopy, but it's a time domain or frequency domain, infrared with a multi-dimension. There we can figure out whether it's a jump diffusion or continuous Brownian diffusion. So again, beautiful stuff.
Okay, sir. I'll take up the next one. How heterodimeric active protein like insulin is stopped in hexameric form, and at what stage of its action it happens?
No, when it is created in pancreas, a pancreatic cell inside, then it is immediately forms hexamer. It is stored as a hexamer. Coming out of the cell, pancreas, it becomes dimer. What holds it together, people believe, is the following, and these are from protein data bank. There are 2 zinc, doubly charged zinc on the 2 top, and there are lots of histidine. There and so 4. So these water molecules are hydrogen bonded. 6 water molecules are hydrogen bonded to glutamate and histidine, and 4 water molecules are free. These water molecules all exchanging among themselves. Those who are hydrogen bonded to histidine are also mobile, and they come back and forth. That adds to the stability and entropy. And so it is a story we put together. I told you it came out, and then CNN News did a wonderful job on that how the movie didn't work. But you would have seen if water is removed, how insulin hexamer collapses. So stability is because of the zinc ions and the water molecules, 10 water molecules. So it's like Agatha Christie's famous novel, 10 Little Indians. So I never figured out why he called them Indians. Then he changed it to 10 little dolls. But here 10 little water molecules hold the insulin hexamer together.
Okay. I'll take up the next one, sir. What is the time scale of electron solvation in water solvent? Is it in femtosecond or picosecond? And the last part of this question is, does it correlate with dielectric relaxation of water?
Ultra fast part of, fast part of electron solvation there involves contribution from quantum nature of the electron, but it is in femtosecond. There is a slow part of 20% or so, which are 10-20%, which are in the picosecond, but not more than 1 picosecond. There is a component very small, people are measured about 8 picosecond, but yes, it is all over within a 1 picosecond. Slow part, this 1 picosecond part, it directly correlates with the dielectric relaxation. Initial part has a much more complicated history, much more complicated story where dielectric relaxation is involved, but it is the optical dielectric constant. The very far, remember the dielectric constant of what is 80. Now you decompose it. 80 to 5 is brought by rotational relaxation that we are talking. Then 5 or 4.86 to 2.26 comes through hydrogen bond excitation, this COO, this, because it's hydrogen bonded. So there is oxygen with the hydrogen, middle hydrogen. They do like this hydrogen bond excitation, which shows up the Raman active mode at 200 centimeter inverse. That brings you 4.86 to 2.26. 2.26 to 1.8, which is n square, refractive index square. That is through libration. So in the ultra fast part, it is the libration and the hydrogen bond excitation that dominates. And dielectric relaxation is mostly the last part.
Okay.
This is well known. In my book, Molecular Relaxation Liquids, I described it very well. There are many papers, a very famous Biman Bagchi paper, and that is Biman Bagchi paper, 1990, early 90s.
Okay. Okay. I'll take up the next one.
Yes.
There are 3-4 more, so I'll take up them one by one. The first one is, how can single molecule spectroscopy help to improve imaging techniques to study of the distribution and arrangement of tau proteins in Alzheimer's disease? Alzheimer's.
The way people do, I cannot give you the specific answer, but I can give you the answer, general answer or semi-specific answer. The way single molecule spectroscopy by and large works is using the Foster energy transfer, FRED. So you impregnate it with a donor and acceptor at different distances. And then you start. The person who did a lot of work on this is Harry Gray from Caltech. Now, or many other people have done. So now, if I could do this biotechnology and construct donor and acceptor, tryptophan and some other things and cyanide dye, then I can know the distance from the rate of disappearance of fluorescence. I can know the distance. From the lifetime of fluorescence, I know the distance because Foster energy transfer is one over R6 dependence. R is the separation with donor and acceptor. That's why Foster energy transfer of rate is called spectroscopic ruler. It's a beautiful term. Exactly, my whole talk would be called spectroscopic ruler. Ruler is length and spectroscopy is time. So through that spectroscopic ruler, putting in different places, just like you put scale in different places and measure the distance, you put in different places and use the time, lifetime to get the length. That's how we do experiments.
Okay. I'll take up the second last question now. When a very low dose of ionizing radiation traverses through a salt solution without breaking a bond, what parameter of water or salt is measurable to tell that yes, the radiation has traversed the solution?
This is a very well-known problem in radiation chemistry. In a general sense of the context we are discussing here, I would need to know the frequency. Depending, see, these questions when people used in 1968 in radiation chemistry, there's a guy called, actually, an Indian guy called Mazumdar, who did a lot of work on these things. And another person involved is the great Unsagar, Lars Unsagar. So when ionization goes, it can ionize molecule. That's what people try to do in radiation chemistry. And because it can damage your body and other things, a lot of chemistry and biochemistry can happen. So knowing the frequency, you would be able to tell. It's a very old classical chemistry. And so it of course, radiation couples. Depending on frequency, it couple it frequency is high. It can couple to vibration. It can even excite and electronically, or it can low infrared radiation. Then it will wage vibration and libration. So it's a, this question almost seems to be coming from before 1968. 1968, 69, when we didn't know the rest of the last 50 years of huge progress has taken place. So the question is framed almost 1968, but it has to be framed differently now.
Okay. So I'll now take up the last question, sir. That's a combination of two, basically. The first one is related to machine learning, and the student is asking that can you highlight a few points of importance of machine learning in theoretical chemistry?
See, I give you a very specific example of machine learning, which has been around for quite some time. We have been using for 30-40 years in the following sense. For example, let's see, I want to know the bond breaking, the kind of things our Karplas, Warshel, and Leavitt got Nobel Prize for. So now I want to know about the environment of, by using, I told you, two-dimensional IR spectroscopy. I want to use the OH bond. I replace it by deuterium so I can separate it out. So the OH frequency is 3600, OD 2500, 2600. So that stands out. Now I want to know how does it behave in response to fluctuations, because that is necessary to time scale of reaction. What do I do that? If I try to do a full simulation, it's very difficult. So what we do actually is the following. We run some simulations, then we make a master plot. And that master plot is now used for subsequent calculation. This is exactly machine learning, neural network, that you train by certain experiments from microscopic, and then you do it for more longer time, slow things. Like I can tell you one more example. We have two simulation techniques called molecular dynamics and Brownian dynamics. Molecular dynamics, when each molecule is interacting with a detailed microscopic potential. Brownian dynamics, however, has much less information. So we do molecular dynamics to learn about diffusion constant, viscosity, potential energy surface. That is machine learning. Then we use that to run a Brownian dynamics. See, these big things of artificial intelligence we have been doing for a long time. It's just some fitting, essentially, at some level. It's trivial. Coding might be difficult, conceptually trivial. Don't get fooled by these things.
Okay, sir. So I think that we have taken up nearly all the questions. And thank you very much, sir. And on behalf of the National Academy of Sciences India Delhi chapter and the host institution, Deen Upadhyaya College, I would like to thank you for sparing your valuable time. And I also would like to thank all the attendees. I just randomly checked. There was around 350 plus, and now they have, I think still there are about 250 plus. They are still there. So the exact number I'll be able to come to know after the webinar itself. So any concluding remarks from your side, sir, then I'll close the session.
Yeah. I essentially want to tell you one thing that, and these books that I have written on the how to be successful in higher academia, I have said one thing repeatedly, that this is for students, that you should really have a little bit still, however difficult situation is, have a little nobler goals and prepare yourself. You have only yourself to blame at the end of the day, because okay, India is a very difficult country, because when you started it was so difficult. You don't know how difficult life was. I don't want to go into that. Now life is somewhat better. Of course, getting job is a little bit more difficult now than our time probably. But you should never lose heart, and you have to prepare yourself. And one of the major things of preparing yourself is to read a lot. Learn to write. Yeah, I find most of my students who don't do well, they're poor writers. And how to become a poor writer? You become a poor reader. So read a lot, write a lot, and then remember these famous lines of last poem of Rabindranath, that path to creation or any kind of creative intellectual world, life is difficult. But you don't get reward in terms of money, fame, but you get reward in terms of doing at the same time. I'm trying at the end of my career. I've worked on now many years, more than 40. That the ultimate reward at the end of the day is really work. That I myself gave up that hope. I saw many politics, many things going around, which was very, very sad. But I now really understand what Winner said, that nobody should be, you should not allow yourself to be disturbed by too much what is going around. It's very important that you don't get disturbed.
Thank you. Thank you very much, sir, for these enlightening words and words of wisdom, which is very much needed right now during this pandemic when all of us are back at home alone. So your words of wisdom will definitely motivate students to take up various challenges in their future careers. Thank you very much, sir.
I really want last word that he did it wonderfully well, and I am really grateful for you.
Sure. Thank you. Thank you very much.
Okay. Thank you.
Thank you very much, sir. Okay.